Hi, and welcome to Lecture 29 in this Introduction to Proofs course. I'm Joe Fields. We're going to be covering Section 6.1 in A General Introduction to the Art of Mathematics. JIAM is how I usually prefer to call it. That is an intro to relations. Now, we've previously seen relations back in Chapter 1, but this is going to be a bit more formal. So, moving in the direction of more rigor. Here's the outline for today. We're going to have some introductory remarks. Then, in this attempt to get more rigorous, we'll define Cartesian products and talk about how to view relations in that context. Then we'll go over notation, and finally, some things you're familiar with from dealing with functions, composition of functions, and inverses of functions. Those are well-known operations in the functions world. They have their versions in the relations world. So first, what exactly is a relation? Well, let's just focus on symbology. When sometimes you put a symbol in between two numbers and it means do something. Other times it means check something. For instance, if you put a plus sign in between the numbers 3 and 4, it means add them. Of course, you get something numerical when you do that. You get 7. On the other hand, if you put an equal sign between 3 and 4, I know they're not equal, but it really does mean this. Check to see if they are equal. And the answer is no, they're not. So you actually get a Boolean thing. You get a false value from evaluating that relation symbol stuck in between the numbers. Most of the relation symbols we know so far have numbers on either side. That's not always the case, but here you go. Equals, not equals, less than, greater than, less than or equal, greater than or equal. But also the divisibility symbol, that vertical bar. Those are relation symbols that have a number on either side of it. On the other hand, we know some things that are not numbers. When we talked about sets, we came across these things that are relation symbols, the containment symbols and set equality. I noticed that there's an equal sign here and there's an equal sign here, but really they're kind of not the same equal signs. They're typographically indistinguishable, but one is going to be used to indicate the equality of sets, having all the same elements. The other is the equality of numbers, having the same numerical value. This kind of thing, where you have the same sort of thing on both sides, is known as a homogeneous relation. You can have other things. Well, actually, so far we only know one of these, but there's one relation symbol. See if you can think about this, where we put different things, different sorts of entities on the two sides of the symbol. Yeah, it's the element sign. You see, on the element sign, you've got set elements on one side, and you've got sets on the other. So they're really of distinct types. The terminology for that kind of relation, where you don't have the same things on either side, those are called heterogeneous relations. Homogeneous and heterogeneous are words that get used quite a lot in mathematics in different settings. So maybe it's a good idea to look them up and figure out what they mean. Find a dictionary and see what it says about them. But more or less, homogeneous means having all the same kinds of things, and heterogeneous. There are people who pronounce it heterogeneous, but I kind of prefer the heterogeneous pronunciation. Anyway, that means things are mixed up. There's a variety. There's diversity in the thing, whatever it might be. Okay, so one of the things I find useful, because personally I have a very visual mind, I like to visualize things. So a good way to think about visualizing relations is to use arrow diagrams. I'm going to show you a visualization for the divisibility relation on the set 1, 2, 3, 6. Notice that terminology I just used, on the set, which means it goes from the set to the same set. That's typically how you discuss things when you're talking about a homogeneous relation. There's the picture. You've got the numbers 1, 2, 3, 6 on the left and the numbers 1, 2, 3, 6 on the right. And by the way, that's very non-standard, right? When you have a Venn diagram, usually, if there's one set, there should be one loop around everything. So Uh, the problem is that a diagram like this becomes very crowded when you try to put it all on one thing. So I've made two copies of the set and show the arrows going from one copy to the other. What can you see about the relation from this diagram? Well, there's a couple of things that are interesting. Notice how 1 has arrows that leave it and head to every other number? That's that's a visual representation of the fact that 1 divides one divides everything in the set. Uh, the fact that 6 just has a single arrow going from it to itself, that's a visual representation of nobody else divides 6 but 6 in this collection of things. What else can we see? I don't know. 2 is interesting that it doesn't divide everything, but it does divide the things that are even over here on the right. 3 divides 3 and 6. Makes sense. There's something about this that I really want to make sure people notice. If this was a function diagram, there would only be one arrow leaving each input value heading to the output side. It's perfectly fine for there to be multiple arrows, in fact, one going to multiple places. Just fine when you've got a relation, but when a function, that wouldn't be the case. Let's talk about visualizing the element relation. It is an element of relation which goes from the set 1, 2, 3 to the power set 1, 2, 3. Looks like that. And there's a lot you can see from this too. It's a couple of things are interesting here, I think. One is the empty set doesn't have anybody pointing at it. Why is that? Well, it's because it doesn't have any elements. if it had somebody pointing at it, it would mean that thing was in it, and it doesn't have anything in it. So yeah. The singleton sets the singleton set 1, the singleton set 2, and the singleton set 3 each have just a single arrow pointing at them. Makes sense. They have one element. In fact, the number of arrowheads that land on a set tells you how big it is. It's interesting to note that each of the things on the left has 4 arrows leaving it. There's a sort of regularity to that. 1, 2, 3, 4. Yep, 4 coming out of each of them. Why is that? Well, because each element is in a is paired with the possible subsets of a 2-element set, the complement, right? So the things that could pair up with 1 are nothing else. In other words, the empty set, 1 and 2. So that's like adding the singleton set 2 to the set 1. What else do we have? 1 and 3. That's adding the singleton set 3. And finally, 1, 2, and 3. That's adding the duplo set 2, 3 to it. So you can see that if you took the things where the arrowhead lands on a set over here, coming from 1, and you remove the 1s, you just get the subsets of 2, 3. Okay, I'm beating a dead horse there. Let's move on. The final slide here, I'm trying to be a little bit humorous. Math humor is weak, but the point is to think about the identity. What is it that determines the identity of a relation? And when we think about sets, what determines the identity of a set is its elements. So remember the roster form for a set? Many people, I'm probably in this camp, would say the best way to describe a set is to give its roster form. That gets tough when the roster form is infinite, but still, in principle, we can do those things. So how does that translate into relations? Well, you should try to do the same thing. The identity of a relation is literally, it's kind of weak to say it's tied to. It literally is the set of ordered pairs that make it true. So, for example, if we look at the the relation we just were looking at, the divisors of 6, here's a great way to express that. List all the pairs. Notice in this version of things, there's only one pair that begins with a 6. But there's lots of pairs that begin with a 1. There's only 2 pairs that begin with a 2, and only 2 pairs that begin with a 3. So that roster form listing of the ordered pairs that are in the relation makes this very useful connection between relations and sets. When you need to prove things about relations, the best way to do that is usually to think of them as sets of ordered pairs and then use your set theoretic machinery. Okay, so now we're going to head into being a bit more formal about what relations are. Effectively, I'll say this before I advance the slides. Um, we think of relations as being sets of ordered pairs. Where do ordered pairs live? Where do they come from? Cartesian products. Oh, I was supposed to advance the slides. Yeah, since relations are best understood as sets of ordered pairs, we need to know about ordered pairs. And the xy plane is probably the best example of such a thing. Typographic note, that is an M dash right there, not a minus sign. So I'm not talking about the x minus y plane, but the plane that is determined by the x and the y axes. Okay, so we're going to do a little digression about the famous French philosopher and mathematician René Descartes. If you've heard this phrase that's in the title of the slide, cogito ergo sum, that's the Latin version of his most famous pronouncement in philosophy, which is translates as "I think, therefore I am." You heard that said before? This goes back to this guy. He's an interesting character. So to do this digression, I want to pull up a thing called the History of Math Archive. This is, oh yeah, it's called the MacTutor History of Math Archive. I probably should go home in this thing and show it to you. This is the landing page when you go to look at the MacTutor History of Math Archive. There are hundreds of biographies of mathematicians and then articles about the kinds of mathematics they did. Lots of different ways to access the information. Since we know the name of the dude we're trying to talk about, we're going to biographies, and it begins with a D. Notice you can jump to sections. So since there's a lot of D's, let's jump to the DEs. There he is, Descartes, Rene. So back where I just started. He's an interesting character in a lot of ways. He was, let's see, born in 1596. You know, that's seriously ancient history. Hundreds of years before the birth of the United States as a nation. Well, close to it. Anyway, he was born in France. It's I think it's interesting. His the town he was raised in or born in was called La Haye, and now it's called Descartes. They changed the name of the town for him. Um, his parents were both rather well-to-do people. His father ended up being, what do they say, a counselor to the it's effectively the Congress of that region of France. And his sad thing, his mom died when he was just a year old. She was having another child, and it was not an uncommon thing for women to die in childbirth in that era. So she didn't make it, nor did the child that she was bearing. Um, his father then, not long after, remarried and had some other children, but Renee ended up living with his grandmother and was raised by her. I think this is a very kind of a sad upbringing. You know, both mom is gone and his father went elsewhere and left him with grandma. I'm sure his grandmother loved him and everything, but it's, you know, you can see why he might have turned inward. Um, at the age of 11, he goes to school. The first time, you know, outside being trained at home, I suppose. He did have educated godfathers. So they probably schooled him in letters and beginning of math. But anyway, I picture the school he went to as being a little bit like Hogwarts. If you're a fan of Harry Potter, this is a bunch of kids living there. They're boarders and living together. And Rene had this special dispensation that was given to him because of his sickliness. Several people think that he may have had tuberculosis as a youth, and he just eventually recovered from it. But which is a hard thing to do. It's without proper antibiotic treatment, it's difficult to recover from that disease. But he apparently did. Anyway, he was sickly, and so they let him stay in bed till 11, and everybody else had to get up pre-dawn and do stuff, right? go to prayers, go to clean, do chores and stuff. He got to stay in bed till 11. And there's a point in the biography where it says that he continued this habit of staying in bed till 11 until the year that he died. uh, I he's a man after my own heart. I'm really not a morning person. I mean, I'll get up if I have to, but I'm not sure if I want to sleep till 11. But that's pretty late. Anyway, he uh, he became a soldier at one point and worked in. It mentions it here. Becoming a volunteer in the army of Maurice of Nassau. Well, he there's a story about when he was an older man, probably in his 50s. He was taking a boat to an island off the coast of in the North Sea, and uh, the guys who were taking him spoke a language that they thought was not going to be known to him, and they were planning to ditch him, throw him overboard, and steal all his belongings. And Descartes, being a former military guy, and this is military in the days of like sword fighting military, uh, whips out his saber and says, "No, you're not. You're going to take me where you were supposed to take me." Yeah, I'd love to know whether that's a true story or not. It's recounted in this book called Men of Mathematics, which I read as a child and thought was really cool. Anyway, in the end, after doing lots of interesting things for math, he got an appointment to become the personal tutor to the Queen of Sweden, possibly when she was just the princess. Oh, probably should look it up and see what it says in here. Uh, there's so much information about his life. Okay, well, yeah, Queen Christina. So she was already queen. She persuades Descartes to come to Stockholm, um, and she wanted to learn about calculus. And well, sorry, not calculus. The precursors to calculus. They phrase it in here. The queen wanted to draw tangents at 5 a.m. So he stopped getting up at 11 and began getting up at 5 for the queen, and it killed him. He didn't last from that. Okay, so the climate in Stockholm is not what he was used to in the south of France, but also I'm voting for the breaking his lifelong habit of getting up late. Uh, so why is this guy so important to us now? It's not the "I think therefore I am" quote. He is the guy who united two completely different branches of mathematics. He took geometry, which had been considered to be a completely separate thing, and algebra, and put those fields together by realizing that points in the plane weren't just marks you made with a pencil. You could locate them with an x coordinate and a y coordinate. I kind of imagine he was lying abed as a sickly youth, looking up at a tiled ceiling, and just had this insight that, if you see a bug crawling around on the ceiling, well, you can keep track of its position by counting how many tiles over and how many tiles in the other direction. Well, as long as you have two numbers, you can locate that point. That's that's a weird to me that such a fundamental insight, something we're so used to, wasn't something people knew, or it wasn't obvious at first. It took Descartes coming along to see that. And so consequently, the idea of the xy plane is actually called the Cartesian plane in his honor. And more generally, you can make ordered pairs, not just of real numbers like you have for the xy plane, but out of any pairs of sets. So that's what the Cartesian product is all about. It's in generally what we talk about is the Cartesian product of sets, but in the particular instance, the Cartesian plane, we're talking about the sets being the real numbers. Where are my slides? I took them away. There we go. All right, back to looking at things. Um, Here's the definition of the Cartesian product of two sets. And by the way, notice this old school usage of the cross sign that you did in elementary school, probably for multiplying. A cross B, that's how you read it. What it is the set of all pairs, A comma B, putting them in round parentheses, right, to make a thing that looks like a point, where the A comes from big A and the B comes from big B. So that's the set of all ordered pairs where the first element is in A, the second element is in B. Oops, not too fast. Oh, I see. I've got to skip over in the pause bit here. Anyway, the special case where A and B is R, that's the Cartesian plane or the XY plane. Notice there's an analogy you can make with ordinary multiplication, and that lets you think about the powers of a set, which is not the power set, but literally raising an exponent on a set. So R2 is how that's pronounced, hence this joke. That's how they spell the name of R2-D2 in the Star Wars books, if you read those. R2 is R cross R. R3 is R cross R cross R. Anyway, the generic deal, any subset of a Cartesian product, that's what a relation is. Not any particular, I gotta say this more accurately. If you give me a subset of a Cartesian product, you've actually given me a relation, and vice versa. If I have a relation in mind, I can tell you what subset of a Cartesian product that relation is. Okay, notation. The style of notation we've been talking about, like with the plus signs going in between two numbers and the relation symbols going in between two things, that's called infix notation. There are other options, maybe not as common. I'm kind of used to these TI calculators that have infix notation in them. If I do 1 plus 2, the answer is going to be 3. I put the plus sign in between them. A different style of calculator when I was a kid was made by Hewlett-Packard, and it used a reverse notation where you'd put in the two numbers and then you'd hit the plus sign. That would be postfix notation, or in those days they called it reverse Polish notation. I don't know why. Maybe Polish notation had the other possibility, which was you might put the plus sign up front and then list the two numbers. Anyway, infix notation is the technical way to refer to what we're doing here with a symbol going in between its arguments. If you've got an abstract relation on a set S, it is literally just a subset of S to the second power. So what I've written right there is a relation symbol, R, is a subset of S cross S. So how do you deal with the notation when you don't have kind of a real relation, but rather you have some arbitrary relation? Just use the relation's name the same way you would if it was a less than sign or an equal sign. Stick it in between things. So if you write ARB, I should mention that a lot of people, if you want to be more specific, you say A is R related to B. Although if you're doing a lot of these, saying ARB is going to be obviously shorter and preferable. Anyway, writing ARB like that with the R in between the A and the B, that means the pair AB is one of the pairs that's in the relation R. It's one of the things that makes it true. Okay, some more formality. We're going to start thinking about two sets, although they need not be distinct. And an arbitrary subset R, which is contained in that Cartesian product. So the relation ARB, the relation R is defined by A is related to B if and only if the pair AB is in R. That's literally saying that the relation is the pair. Again, maybe I'm beating a dead horse on that point. Some more terminology you need to know. A is called the domain of R, and B is called, not the range, it's the codomain of R. There is a distinction between the sets A and B and the subsets of those sets that actually appear in the ordered pairs in R. And I didn't make a slide for this, but I wanted you to see a visualization of this. All right, so sorry. This is this like super old school drawing program that I use on my Linux machine to make diagrams for things. And what we're looking at is a set A and a set B and a bunch of arrows that go between them. Let's point out that there's the things where arrows leave from, and then there's the things where arrows land. And presumably there's other stuff in A that doesn't have an arrow leaving it, and there's other stuff in B that doesn't have an arrow landing on it. So while A is called the domain of the relation, what you're used to when you talk about the domain of a function is this interior set. It's the set where the things are defined. So there's some different terminology people use. Some folks will say the domain of definition versus the domain. I kind of like the phrase active domain. But when you've got a relation, there's a distinction between what's the first, where do the first things in pairs come from versus what first things actually arise amongst the pairs. So we have the domain and the active domain. We have, even in the functions world, we have this other distinction. B is the codomain, sort of where things are being aimed, but the range is the set of things that actually arise as the outputs, right? So the inner set here is range, outer set is codomain. On the left, both things get called domain, but domain without a qualifier and either active domain or domain of definition for the inner thing. All right, back to the slides. Okay, what is this? Oh, I'm trying to give us more practice with looking at set notation and seeing if we can decipher what it means. I've got a set builder notation thing here for something. What is it? Well, it's the set of things from the set A such that there exists a y in the set B and xy is in R. Okay, so what I've defined here is the set of x's that actually appear as the left-hand elements for some y. There's a x that gets sent to it. That's called the active domain, or as I said before, domain of definition. So my caveat about functions, in effect, I already made this. With functions, we don't usually distinguish the set A, but really just talk about the domain as being this thing that I've defined right here. The x values for which there is a y value. Okay, I know you've already said this too. The codomain side, that's the right-hand side or downstream side, if you're thinking about the direction of the arrows. We have a similar idea. The things that actually appear as right-hand elements in some of the ordered pairs in R that's called the range. The special case of functions is and I find it's disturbing to me, in fact, that a lot of times people introduce this idea of relations to students who are not really ready to see it, and then say, well, a function is a special kind of relation that satisfies this property. Really, functions are an easier concept, input and output, right? Why? But anyway, that's the tendency in pedagogy today. So what is this additional property that functions have, which makes them a special category of relations? Basically, it's the vertical line test, which I'm sure we all know. If you've got a function f, I am thinking right now of a real valued function of a real variable. So the sets A and B are both R. You could presumably write xfy to mean that x gets mapped to y by the function f. That would be the relations way to say what f is doing. But that's not something anybody does. The whole world uses this notation that was created by Leonhard Euler. Ooh, this is another chance to go to the history of math page, but I think I'll hold off and let you follow up on that if you'd like to. Leonhard Euler was a very famous Swiss mathematician, possibly one of the best mathematicians of all time. Lived quite a few years after Descartes, so they would have been contemporaries. Anyway, so we use Euler notation. This is the y equals f of x stuff that you're very familiar with. But what does y equals f of x mean when you're talking about a function as it being a relation? It means the pair x comma y is in the relation. You may also think of it as the pair x comma y is a point which is on the graph of the function. So the graph is the function in a certain sense at this point of understanding things. The graph is a set of points. The relation is a set of points. The function, you may have been told it's a rule, but now you think of it as a set of points. Okay, so now finally we're going to end off by talking about these things that are first created or first thought about when you dealt with functions, composition, and inverses. Couple of operations. I know you're familiar with these. Composition is like when you hook the function square root of x and 3x plus 1 together, and you get the square root of 3x plus 1. Let's see, which function happens first here? The outer thing is the square rooting, and the inner thing is the 3x plus 1ing. So we're doing that second function first and then applying this one. Okay. If you do this in the other order, you get a different thing. And that's kind of an interesting setup, right? There's a little bit of a tendency to think order doesn't ever matter in math, but there's a lot of situations where you've got to be cautious about changing order. If you do this composition the other way around, you first square root x, and then you stick that square root in where the x is in this other representation. So you get 3 times root x plus 1. Inverses are this, I'm sure, a well-known concept to you too. You remember how e to the x and ln of x are inverses. What one does, the other undoes. Both of these things make sense for relations. So we define them for relations. What are we going to do first? Oh, the inverses. Okay. So if you think about the input-output pairs that happen when f and its inverse are applied to numbers, you have things like this. If f is applied to a and you get b, then if you apply f inverse to b, you're supposed to get a, right? You're supposed to take b back to where it came from under f. The inverse is supposed to do that. So that means the pair in f is a comma b, and the pair in f inverse is b comma a, and vice versa. Well, yeah, that's because the inverse of the inverse is the original guy. Okay, so if we write this with infix notation, it would look like that. I know I've already said we don't do this, right? But just for the moment, think about it. The pair AB is in F, the pair BA is in F inverse. So yeah, there's a couple of ways to say this. If you have a relation R, you can define its inverse using the infix notation. If A is R related to B, then B should be R inverse related to A. Or you could talk about the pairs. R inverse consists of effectively the same set of ordered pairs that R does, but with the order switched. So not really, but kind of. See how you have BA such that AB is something in R. There's probably another way you could denote that by saying BA is an element of R inverse if and only if AB is an element of R. Kind of felt like it was cheaty for me to just say that last bit. So here it is written out. I can barely fit it on the screen, but the pair AB is in the relation if and only if the pair BA with the term swapped is in the inverse of the relation. Okay. All right, what's our next slide? Okay, we're going to start finally wrapping things up by talking about composition. When you think about the composition of two functions, remember how that works. You have f of g of x, and you're going to first compute g at x, and then that's going to be a new value, right? It's not going to be x, it's going to have been modified by the function g. And then after you get that, what people call an intermediate result, you're going to apply f to that. So to compose two relations, we're basically going to think about the same thing. We want an intermediate result, and then we're going to apply the second relation to that. Here's the picture to keep in mind. You're going to usually, in the generic case, have 3 sets, although they could all be the same, I suppose, too. But in the heterogeneous case, you'll have A, B, and C. And there's a relation R that goes from A to B, and a second relation S that goes from B to C. And you're chaining those together. Okay. There is a reversal of order that we need to watch out for. I think I've said this once or twice. But R is going from A to B, and S is going from B to C. Okay, we could say that in terms of Cartesian products too, that R is a subset of A cross B, and S is a subset of B cross C. Still, the composition ends up going from A to C, so it's a subset of A cross C. So is the thing we're picturing R composed with S, or is it S composed with R? Well, the thing to do is to think about the function. Wait a minute. Let's go back to the previous slide. That thing we're picturing, is that ROS or is it SOR? Um, yeah, it's temporally, that is, as the flow of time works, we're first applying R and then getting an intermediate result and then applying S, getting the second element in our pair. Okay, so think back to how functions work. When you did the function f of g of x, it's f of g of x, and in that order, it's g that is applied first. Right? G is on the inside of the parentheses. So this is backwards. When you read it in the ordinary way, f composed with g, it makes you think f happens first, but it doesn't. G happens first. So the upshot of that is you should read compositions from right to left, not left to right. So the one we've been looking at being R first, it's actually SOR. Watch out for something. There are a small minority, but still a substantial number of books that will use composition written the other way around. That is, they'll make it seem natural going reading it left to right. Just be aware that this happens, right? Different people take on different conventions, and you just need to be aware of that convention. Okay, yeah. So most of the time, and all of the time in the book you're currently working your way through, we're going to read our compositions from right to left. Okay, here's the formal definition. Well, here's the prologue to a formal definition. You need R to be a relation from A to B, and S is a relation from B to C. Then S composed R is a relation from A to C defined by this. Well, it's not as bad as you might think. SOR is a relation, so it should be a set of ordered pairs. Those ordered pairs come from the Cartesian product of A and C. So we're looking at things that of the form AC as an element of A cross C. Here's our intermediate result. See how it's existentially quantified in the set builder notation? We've got this existential statement that decides, are you a member of this set or not? If there is a B so that AB is in R and BC is in S, then that AC is going to be in SOR. I think that works well when you pull it apart into little pieces like that. You can express the same thing using the infix notation, which looks kind of like this. I personally need to put some parentheses around S composed R to think of that as a single relation symbol, but I've seen places where they don't do that. I don't know. To me, that looks better. But anyway, A is S composed R related to C if and only if, again, the existential quantifier, there is a B in the intermediate set B such that A's are related to B and B is S related to C. Same idea. Let's wrap things up by looking at something. I hope come here. Oh, jeez, it keeps fading. I had something else open and I've closed it. Hold on a second. There it is. Okay, so look at this exercise from the Giant book. It asks us, well, first of all, it sets up a couple of relations and three sets. Let me just quickly review what's going on here. The first set A has numbers in it, 1, 2, 3, 4. The second set has early alphabet letters, A through D, and the third set has late alphabet letters, W, X, Y, and Z. Okay. And then we've got relations, R going from the first to the second, and S from the second to the third. So are we looking at ROS or SOR in this case? In this, the way this composition is drawn out, you see the chaining of things. Yeah, this would be R first and then S, which is reading right to left, that one. Okay. So it says ROS is impossible. Why does it say that? Well, because the codomain of S is these four letters, W, X, Y, and Z, and that would need to be the domain of R if we were to compose it in the other direction. So that is, if you stick an early alphabet letter into S, you get a late alphabet letter, and then you're try to stick that into R, but R's inputs are numbers. It just breaks. It doesn't do that. So that composition is impossible. The second composition, though, well, the second part of the question asks you, what is the only pair in this composition? Now, there's a lot of pairs from the first to the second set, and a lot of arrows that go from the second to the third set. But there's only one place where we see an intermediate value, an intermediate result, and it's right there. It's that A, where 1 goes to A, and then A travels on to Y. So the one pair that's in this composition is 1 comma Y. Pointed at Z while I was saying Y. 1 comma Y. Okay. Okay, that is it for this lecture. I would advise you, if you're continuing to go through these videos, that it's a great idea to read the lecture, read the section first, then watch the video, and then maybe even go back and read it one more time. You really cement your knowledge by multiple exposures. And even if the first pass through, like, I know personally, I often tended to read my math books in the later evening and end up falling asleep because math that can be a little uh, dry. Um, Even if you don't get much out of that first pass, you're getting something. You're getting your brain to be exposed a little bit to the stuff you're after, and so the next time you go farther in your understanding. And multiple passes is really an important part of learning. So here's my recommendation: is now that we've gone through this, go back and read 6.1 and then do a peek ahead and do 6.2 if you're planning to look at the next lecture. Anyway, have a great rest of your day, and we'll see you next time.